Okay, okay. Thank you very much for the introduction. We'll talk today. I will start talking today about experimental investigation of composite materials. Hopefully, we can reach joints. If not, it is also scheduled for the Thursday meeting, because there we'll talk about fracture mechanics. So we'll see how it goes with the lectures. But we will cover anyway all these topics as agreed. Before we start, I wanted to share with all of you the links to join or to see our activities in the European Society of Composite Materials. Professor Bedi yesterday mentioned that I was presiding this society for a couple of years, and now I'm there as a past president. But this society is very active in composite materials. We call it European Society because it has been established and is run by European scientists and engineers, but it is open to everybody in the world. So I'm sharing the LinkedIn page of this society if you want to follow up and know what we are doing. And I will also share, I think you can already find it in the LinkedIn site, but I will share also with you the webpage of the society, this escmeu.org, where together with the activities, we also have a tab, a page that announces regularly positions. So for those that are interested for PhD positions, postdoc positions at the European level, you can visit the web page and check what can be found there. At the point now that we are talking, the web page itself is under construction. We try to implement these job offers. But we announce regularly open positions on the LinkedIn page. So there you can check. And if there is anything interesting for you, you can of course contact directly those that are announcing the positions. With this, I will stop this introduction to the European Society of Composite Materials, and I will share my screen to start the lecture of today. I hope you already see my screen. Should be full screen in a minute. We all have the full screen presentation.
Yes, it is visible. Yeah.
Okay.
You can see it.
Okay, so today we'll start discussing about fatigue of composite materials and focusing on experimental. And the objective is to cover composite laminates, adhesives, structural adhesives, and of course, at the end, as already Professor Bedi announced, discuss about composite joints. We have laminates, we have adhesives, and we use these two to make a joint, and we'll try to see how these joints that are critical in every engineering structure are behaving under fatigue. There is someone that is annotating my lectures. If you can please stop. Okay, thank you. So I will start with again some visual representation. Can someone tell me what do you see here?
Torture, sir. Form of torture for.
Yes, it's a torture. Eh? There is a poor lady there that is tortured by these guys. This is actually the Middle Ages in Europe. They were torturing people for several reasons. So again, torture. Eh? What does this mean for you? What is the objective of a torture?
फ्राइड राइस फ्राइड राइस ले लेते हैं फ्राइड राइस
You try to reveal some secrets, no? You
To
try
cause pain, to cause pain to the body, and
But what is the objective? Okay, you cause pain to the body, I agree, yeah? So, okay, we can start with that. You cause pain to the body. What
mental breakdown, and surrender of the
Mhm.
person being tortured.
And what is the result of this?
He
The
will break
bigger
down
message
to-
is to install fear in the larger population.
Yes, and then the result. So the objective, the final objective is to
He
get
will
some
listen to you.
questions,
He
to
will listen
understand, to understand something, to get questions, to get responses to your questions. So, have you ever seen this series? The 24 hours? No? Have you ever seen this? You remember the Minions? This is another series or movie. And then this is, for me, it was very funny when I saw it with my children. I realized, okay, this is a tensile testing. And we torture here the minions, our specimens, and we're asking for
पीस छोड़ा है
Mhm. We ask and we expect to get some responses to our questions. We see how they respond. So this is exactly what we do when we test composites. We torture the composite material. We cause pain, as you said, we cause pain to their body with the objective to get some responses to our questions, to see how they, first of all, to investigate how they fail, if we go to failure, to investigate how damage progresses before we go to failure, and to investigate at the end, when we finally break the material, what is the maximum load that we apply to break the material, how much deformation the material can assume before complete or final failure, and how many cycles, when we talk about fatigue, the material can resist before it fails under specific loading conditions. So this is a link that we already did in the previous presentation about the behavior, or either quasi-static or fatigue of humans and materials. And coming back to materials now, we see that we have, if we follow the arrows from the top left for me, going to the bottom left, going to the bottom right, and then to the top right diagram, we see a complete cycle of material and structural development from the material level. Here we see actually it is an adhesive specimen in the machine, to the subcomponent level. Here we see a bamboo culm connected with a 3D printed connector that is in the machine for testing. We see the famous beam of this the Avanson bridge that we discussed already yesterday, the full-scale testing of the beam. And finally, we see a full-scale testing of a bridge in the lab to simulate the fatigue behavior. To simulate, in this case, we have here, we are simulating the quasi-static behavior of the bridge for the serviceability load. So all these experimental investigations are performed for a specific reason, each one for a different reason. For the bridge, for example, we don't want to break the bridge. We want to see if the bridge can sustain the loads that are supposed to be seen by the bridge during serviceability, during service. We're not going to the ultimate state of the bridge. On the other hand, when we come to the specimen testing, we're going to the ultimate state because we really need to know how much this material can sustain, how much stress this material can sustain. So this is as we said, the analysis that we do, the questions that we are asking to the materials to get the correct responses and be able to use these responses to design correctly our structures and structural components. In these investigations, these are experimental investigations, but they are always coupled by theoretical analysis, either theoretical analysis for the simulation of the material performance, which is what we also discuss or describe as descriptive modeling, or theoretical analysis or numerical analysis, or whatever this can be, related to the prediction of the material performance. And this is what we describe also as predictive modeling. So today we'll see a lot of experimental results regarding composite materials behavior. And we will also try to go more deep, mainly tomorrow, about discussing about this predictive and modeling tools that we have for composites. So, testing. Let me open. Oops. We start with a specimen. This is the main characterization of material properties. This specimen has this size, and it is fabricated, manufactured in this way, because for a certain reason. Can you tell me why this specimen has this size and this type, and we have also these aluminum tabs at the end, and so on? Who tells me, to rephrase the question, who tells me that the specimen should be like that?
Probably ASTM standards are there, which will tell what
Standards.
to.
I agree, correctly.
Should be.
There are standards. There are standards that define that the specimen should have these dimensions. They should prepare in this way. They should be fitted in the machines in this way. The machine should run the test at these loading rates. You should be careful of that and this, and you should measure this and that. So there are standards that define these experimental procedures. And the reason for following the standards is to be able to create reproducible results. If I do a test here on the same material, imagine that we have the same material, and if you do a test there on the same material, we should be able to estimate more or less similar values. And to do this, we have to follow the same protocols, the same experimental protocols that are recommended, and please keep this word in your mind. They are recommended and not imposed by standards. So standards recommend best procedures for experimental investigation. So in this case here, what I saw is an experimental procedure. I have a specimen, which is a standard ASTM specimen. It's the ASTM D3039, if I'm not wrong, that defines the experimental procedure for tensile loading of composite laminates. And I saw here the experimental results. If we try to read this diagram here, we see two lines. First of all, these are stress-strain curves, typical stress-strain curves, the blue and the dashed red. And we also have cycles for fatigue. In fatigue, we call them, these cycles, we call them hysteresis loops. I will briefly explain here. We'll come back later on this. First of all, coming back to the static, quasi-static results, we see different behavior. And the different behavior there is due to the different loading rate. If you see the loading rate for the blue curve is 1 millimeter per minute. This is the standard loading rate that is defined by the ASTM standard for quasi-static testing of composite laminates. The higher loading rate, what you see with the red line, 30 kilonewton per second, is a loading rate that shows, first of all, that there is a viscoelastic effect on this material. So the rate plays a significant role. And this is a big difference that we have between composites and metals. In metals, you don't have this rate effect. And the second point that justifies, if you want, the selection of this loading rate is that this loading rate is the same loading rate that we have when we do fatigue testing. It's an average loading rate that you can see. When you do, if I start now playing with my annotation tools, when you do a fatigue testing and you are loading the material with a frequency of 10 Hertz, for example, the loading rate that you have, the speed of testing when you go through this spectrum is relevant to this value. And this value, if you compare the loading rate between these two static tests, the fatigue testing is usually, for more or less all the frequencies that we are using, it is usually much, much faster than the quasi-static testing. This is an issue when we try to mix at the end quasi-static and fatigue results. We'll see later on how we do this and why this is an issue. So to go back here to discuss a bit the hysteresis loops that we see in this diagram, what we see is that we have different sizes of the loops. And I put here the number of the stress that is applied every time. So these loops correspond actually to different stress levels. The sigma max is the maximum cyclic stress that we apply to the material. And we can see that when we are at higher stress level, the loop is a bit thicker than the loops that we have at lower stress levels. What is the area in between this loop? We call it a hysteresis loop. And the area between or inside the loop corresponds to the energy that is dissipated during the fatigue loading. Every time that we do a loading, unloading, reloading of the specimen, you remember what we discussed yesterday, we have some friction in the material, and this friction is translated to energy that is dissipated in the environment. So this energy can be calculated by measuring the area of this loop. So we described and discussed briefly, very briefly until now, the quasi-static testing of composites and the fatigue testing of composites. And we've seen here that there is also a viscoelastic effect on the composite material. And to investigate this viscoelastic effect, we have to go and discuss about creep. So probably you all know what is a creep test. It's a test that we apply a certain load and we measure the deformation of the material. So in this case can be a fixture like that, where we fix the material on one side. On the other side, we have a load, which is a fixed load with this applied easily with this lever arm, with the load that is hung here, down there. And we apply we apply certain pressure to the material, stress to the material, and we measure with these LVDTs here. The LVDT is the linear, what is V? Displacement transducer. V is, I don't remember exactly what it is, but it's the linear displacement transducer. And with this, we measure the strain of the material during time. And we can also, during the loading, if we get photographs of the material, specifically here, because we have glass material which is translucent, we can observe the damage that is accumulated in the material during this creep loading. So this information here, the increase of the strain, is very significant for the material, because it shows that even if we design, imagine that if I go back if I go back here, imagine that you design your material and you say that your serviceability load is at 40 megapascal. And according to this, you are safe. You have no issues with the material performance. But then when you see in the creep testing, it might be that with 40 megapascal, after certain number of hours, you might have a strain that it's very high on the material. And this means that you can even reach the strain at failure. So how these two are getting together now, the quasi-static testing, these three actually, the quasi-static testing, the fatigue testing, and the creep testing. This question is more or less responded or visualized in this simple diagram that I have here. First, we see the one on the top. Imagine testing this specimen at a continuous constant amplitude fatigue until failure. Then it fails at a certain number of cycles. Then imagine that you do the same and you test the specimen, the same stress level as before, but then after a certain number of hours or cycles, either you stop the test or you keep a constant maximum load. So you do testing and then you do this. What does this remind to us? What kind of testing is this?
Probably creep.
Yes,
Creep testing.
it's a creep testing. And what is this test? When we unload the specimen and we let it for a certain time without load. How do we call it?
Well,
There is a terminology. We call it the relaxation test. This is creep and this is relaxation. So the question is, or the discussion that we will open is if this number of cycles that we estimate when we load the material continuously equals to the sum of the number of cycles that we can get if we load the material with interruptions. We discussed a bit about this yesterday, what happens with the interruptions. We discussed and we mentioned that this relaxation, sometimes it is beneficial. We now see that creep, with this diagram here, we see that creep might be damaging, but it might be also that is not. So the question mark, what is the relation between these two values, is still there. And this is part of the discussion that will start today after analyzing the first experimental results. So going further to this presentation, I will again open here to discuss a bit with you about the objectives of the experimental investigations. You remember before we said about these questions that we are doing to persons.
Just excuse me, Professor Vassilopoulos. I just wanted to add something for the benefit of the students, especially students in India, for this particular issue that you are referring to, that what happens when you stop the test in between. Normally, why I wanted to interrupt is because it's very important for students who want to do composite fatigue that we encounter that when you specifically work at low stress levels, that the test is continuously running for maybe 3, 4, 5, 6 days. And then students normally ask me that what will happen that if I stop the test and go home and come back after 4 hours or maybe overnight I stop the machine. So this is what they need to know, that it may have an effect that when you stop the test in between overnight and then restart it again. So we need to consider this, that this will have an effect on the performance also.
Thank you very much for this interruption. this this exactly an interruption that makes this recovery. I agree with you, and you know this investigation about the interrupted fatigue loading initiated by our group when we did around 20 years ago, we were testing wind turbine rotor blades in fatigue. And as you mentioned, these tests for wind turbine blades can take very, very long times, because there you try to simulate the actual frequency of air, and usually this frequency is around 1 to 2 hertz, which means that to reach 1 million cycles you need at least 10 days, and to reach more, 5 million cycles, you might test the specimen for more than a month. Specimen in this case is a complete blade. So what we've seen there is that when we were doing interruptions of the testing for several reasons, either for maintaining the testing rig or for doing a modal testing on the blade, when we were reinitiating the blade test, we were observing very, very good properties or much better stiffness, fatigue stiffness for the material. And this triggered this curiosity to see what happens. And this is exactly what we've seen, that there is a significant effect of this interruption. You will see also later on Thursday probably, when we talk about fracture mechanics, for years, even in the standard of mode 1 testing, mode 1 is an opening. You have a specimen and you try to open it and measure the mode 1 performance. And due to the lack of methods for online measuring devices at the time, the standard suggested to interrupt the test, the fatigue test, and open quasi-statically the specimen, take the measurement of the crack, and then continue the testing. And it was nice, it was okay for very brittle materials, for aerospace. But when we switched to materials for civil engineering, for example, that are softer and more ductile, we've seen that there was a great effect of this interruption to the fatigue life of the fatigue and fracture performance of the joint. So I'm together with you. It's a very significant point and needs to be considered in all the analysis. Additional reasons for interruption might be a failure in electricity. Right? We've seen it a lot of times. You put a test there, you go home, and then during the night there is a failure in electricity. You go back next day, you see the machine is stopped, you restart the test without considering this interruption, and this gives different falsified results. And the problem is now it's thank you very much for this. It initiated additional discussions for me. The problem with this falsified results is that at the end, because we are kind of stressed to publish, we publish everything. And I wrote once in one of the publications that in the literature there is a lot of information that is most of the times unintentionally, other times intentional, but I think it's not the majority of cases where we have falsified results. And this is probably another output of this course, to understand that we should not accept whatever we see in the literature, independent of who is the author of the publications. We should always criticize and see twice something before we digest it and we accept it and we use it for our investigations. So I'm closing this small parenthesis. We can discuss again if you wish about that. And coming back to this slide that is actually discussing the objectives of the experimental investigation. There we are questioning the specimen, and we're torturing the specimens to get some responses. And the main topic there, the main question that we have to ask ourselves before even we do the test is, what is the objective? What are we expecting to get from the testing? And I'm asking this, I'm saying this, what is the objective? Because there are different objectives that can be directed to different tests. When we collect data, we might collect data for life estimation. We do a fatigue testing, and we need to know how long the material will stand with under certain loading. So this is what I saw here, life estimation. We don't care about the failure modes. We don't know, I mean, we don't care how the material will fail. We need to know only how long the material will stay there. In other cases, we need to know if the material will stay there under different environmental conditions. This is in structures that work outside, in what we call at the open air. It is important to know if the structures can survive under higher temperatures, when we have wet environments, when we go to very, very low temperatures that in several cases are more critical than high temperatures. And there we talk about the durability of the materials. In this case, we need to perform additional testing. It's not only a life under certain load, but it can be life under certain load at different temperatures. It might be life under certain load at different temperatures and different frequencies. So there you see, every time that we add a parameter, we add the complexity of the testing. And this complexity of the testing, of course, on the paper, it doesn't complicate the things. But in reality, if you add one parameter, it might be that you have to repeat a complete SN curve. And to make an SN curve, a complete Wöhler curve, what we discussed yesterday, you might need more than 15, 20 days. So imagine another curve means another 20 days and so on. Then you have data, you can collect data, quantitative data for performance, and this can be related. A very simple example is data for stiffness. So we measure, remember that we were discussing about life estimation. So we do a test, we measure the load and the cycles, and we have the life estimation. If
Sir,
in parallel,
I have a question.
yes, please.
How do you what do you understand, what can we understand from durability? Like for like building materials, we know durability, like influence of temperature and moisture and all that. For composites, how do you see durability? Like what is the big picture there?
You responded yourself. It's the same. Composites are not coming from Mars. They are materials that we're using like any other material. So the durability of a composite is exactly the same as the durability of concrete, for example. You need to know the performance of the material at the long term. When we talk about durability, usually we talk about the long term. And you need to know the performance of the material at this long term under specific environmental, as we call them, loading conditions. So you can increase the temperature, because we know that temperature is significant for composites. You remember the discussion that we had last time about the glass transition temperature. If you have stiffness and you have temperature, we know that composites are performing somehow like this. Stiffness drops a lot around a temperature which is called the glass transition temperature, the TG. And stiffness and strength, it's not only stiffness, all the properties. And this region here of temperature, we call it the glass transition region. So this means that if your material is loaded at this temperature, so it is in an environment that is loading at these temperatures, it has a stiffness which is much, much lower than the stiffness that it has at ambient temperatures. So, and durability means to investigate the performance of the material at a wide range of temperatures that can tell you how the material behaves in different conditions. We'll see later today, you have also the water that can ingress. So you have here a square of time. So composite materials, especially resins, absorb a lot of water. So if materials absorb water, this water goes inside the molecules, and then it creates plasticization zones that make the material more soft. And this affects, again, the durability of the material. So it's exactly the same. The concepts are the same as in other structural materials. The only thing that is changing actually is the approach that we do, and of course the values. The behavior here, the values, the drop of stiffness is different in concrete and is different with water, for example. It's different in concrete, it's different with composites.
Oh, thank you, sir.
Okay, so I was trying to summarize this performance data for performance, and I was saying that together with stress and cycles, for example, you can measure strain that at the end can give you the stiffness of the material. And if you have the stiffness of the material, you can use it in a way of a quantitative. If you know exactly the value of the stiffness during fatigue, what we call the fatigue stiffness, you can use this as a quantitative measure. And this can be also used for the performance of the material as a criterion. Imagine, very, very simple, you have a wind turbine rotor blade that is rotating, and this blade loses stiffness. And at a certain time, it has lost so much stiffness that the blade, while rotating, it starts hitting the tower. So this is a no-go. There is a criterion tells you that the material is deteriorated so much that it cannot continue anymore being in operation. So this is a performance criterion, tells you that you have to stop. So collecting data is very significant, and collecting good data, collecting correct data that are reliable. And this data should be shared. This is the main point that I wanted to convey here. The databases that we create should be shared so that are accessible, shared with all the information that are needed, and accessible to everybody that want to use this data for modeling. You will see also when we'll start discussing about modeling procedures, it's difficult to find good data to use for modeling. So every time that we collect, we should really collect data and share, either in causostatic or fatigue or creep or whatever is needed. Of course, fatigue is more complicated. And the material properties variate with loading. This is what we discussed before about the stiffness. So there is a reason to collect more data there. And what is also significant, what I have here with highlight, is that the history plays a role. If I give you a specimen and I don't tell you what has been done before on this specimen, you will not be able to create correct data and give good answers for the material behavior. Because if the specimen is already damaged and you don't know, then whatever you measure is not valid anymore. So we need to know the history. We need to know the history of loading on the material to be able to first of all perform correctly the test that we have to perform, and to also conclude correctly what we have to conclude. So how to perform a test? As we said before, there are standards. You suggested that there are standards, and there are a lot of standards for composites nowadays. Here I'm referring to ASTM standards to avoid additional complexity, but there are also other standards. Now, most of people work also with ISO standards, the international standards that are similar to these ASTM standards. There is already even a standard. You see here this last one on the bottom right. That is the standard guide for testing. So it gives information about about how we do the testing, not for specific testing, but how we do the testing. You see, we have standard test methods for tensile properties, for tension fatigue, for fatigue and fracture, and there is also standard terminology about the notations that we'll use. And this is also important because it allows to communicate. When we talk about terminology in a technical discussion, if I mention the fatigue failure, for example, if I call it damaging and someone else calls this failure, then it's difficult to communicate. And this is the reason for having this kind of standards that are actually giving a list of terminology that should be followed by all the researchers that want to communicate in the area. If you see, the standards are very detailed. There are standards for everything. This comes from the standard 4762. So it's this one that tells how, as we said, how to test composite materials. And it says if you want to do, for example, tensile testing to estimate the tensile strength, you have to follow the standard D3039, the one that I mentioned before, that tells you that you need to have a straight sided specimen suitable for random discontinuous continuous fiber composites. It should be tabbed and so on. If you want to estimate tensile strength and modulus, probably you have to go to standard D638, which discusses about this dumbbell, the dog bone specimens, and so on. I will not go through this list, but you see that there is a recommendation, if you like, for any testing and any specific objective that need to be fulfilled. And probably if you take a look on these diagrams that we have here, I mean, this actually it's copied pages from the standard. You might understand that in some cases there are multiple. If I go here, you see there is a standard for this one, D638, for tensile modulus and tensile strength, and it talks about a dog bone, dumbbell shaped specimen, and it's also the standard D695, which is again a similar dog bone shaped specimen that is recommended for, and the differences are here. This is recommended for highly oriented or continuous fiber composites, and this is not recommended for high modulus composites. And you see also in these standards, there is a mention, ASTM standards discuss about the equivalence between, between the ASTM, for example, in the ISO standards, or between the ASTM standards and the military handbooks in the United States, and so on. Because there are, I mean, the procedure for doing testing is not so much different between the standardization procedures. And that's why when it is when there is equivalence, it is mentioned. Okay, I will let you, if you want to check more, you can check this these standard procedures, and you can see what is happening there. I have some more here on the slides, and then I came back to this because there are standard practices for analyzing. Before we've seen test methods for testing describing how we test. And here, this one, for example, the 739 E739 standard, talks about the statistical analysis of fatigue data. So here we have a standard procedure again, which is based on mathematical expressions on how we can analyze this fatigue data. And this is again important to have specific methods to know and to be consistent on the way that we analyze the results so that we present at the end results that can be comparable. So I will open this. This is kind of validation of what we said before. When we do a testing, what do we expect to have? And the response is that we expect to have material properties or material data depending on the needs or the questions that we want to respond. And then we go from the simplest case. Here, if you want to make a kind of ranking here, we go from the simplest case, this one, case one, where we collect lifetime data. In fatigue, we clamp the specimen, we load, so we measure the load with the load cell of the machine, and we do not measure anything else except the number of cycles to failure. So there, it's the simplest case. If we need also to measure stiffness degradation for the performance analysis, as we said before, then we need to measure the load, but also the strain. And there is a bit of okay, I'm asking, how do you measure the strain in a specimen? When you clamp a specimen on the machine, you measure the load by the load cell of the machine, and this is obvious. Then how do you measure the strain?
Strain gauges, you can put strain gauges, or we can use non-contact like DIC, digital image correlation.
Okay, so you have the specimen on the machine.
You can put strain gauges.
Fixed here and there and loaded. So you can put strain gauges here.
Yes, yes.
So then this strain gauge gives you the strain.
At that point, we will get the strain.
Yes, at that point, which is the point of interest, because we know that they're also close to the grips. We have stress concentrations wherever. So we need to go to an area away from the grips and we measure the strain. So you can put strain gauges. You can also, so method one, method two.
DIC, we can use digital image correlation.
DIC, digital image correlation, that gives you the full field measurement of the area. What else? Which other methods? Method number three. I write here, I don't know if you can, or if I write better, I don't know if I can write better, but here we call it a clip gauge. What is a clip gauge? Clip gauge.
Extensometer?
It's an extensometer that you can clip on the specimen. So it's similar to the strain gauge, but it's a mechanical system that you clip actually you attach to the specimen. What is the simplest method to measure the strain? I mean, all these need equipment. So a clip gauge, a good clip gauge might cost $10,000. A DIC system might, with the camera and then the software, might cost more than this. Strain gauges are relatively cheap, but then it's difficult to glue. And you also have problems when you perform fatigue. After several fatigue cycles, they are detached, because it's actually also the glue that is fatigued, and after 10, 15, 20,000 cycles, the gauges are taken out. However, I agree that these three methods are the more accurate to measure fatigue. There is another method that is used. If you
Physical measurement of a broken sample?
No, because this is correct, but this does not give you also the evolution of the strain during the loading. And also what you miss with this is that at the end, when the sample fails, it might recover. You test the sample, you load it, and then when it fails, it goes back. So you don't have the total strain when the specimen is broken. I didn't listen this last one.
लंच में कहा तब कहाँ लैपटॉप लेके जाओ साथ में
Can you explain this method?
I think some persons are doing personal talk. It's coming onto the there's some personal thing, conversation is coming.
सतेंद्र फोन कर रहा है मुझे लगता है सर बुला रहे हैं 1 मिनट रुको मैं इसका फोन लेता हूँ
Someone is having
Okay.
some personal.
Okay, but the simplest method, I mean, the simplest method, if
बुला
you
सकते
see
हैं ना मैं एक
strain,
बार फोन उठा देता हूँ क्या बोलता है 1 मिनट के लिए 1 मिनट
Someone by name Nikesh. Nikesh, some name is there.
look at this. If you open, I mean, if you not if you open, if you check a book of mechanics, simple mechanics, they say that the strain is equals to the delta L over L. The change of the if we assume that the initial material is clear my drawing clear no the material length, the initial length is L here. This is L, and the material becomes with the loading. It extends by this delta L. The strain is delta L over L. So we can simply measure the strain like that by measuring the displacement of the machine, which is also something that is given by the machine while doing the testing. The problem there for these strain measurements, if we do this, we said before that the 3 methods that we described are very accurate. The problem if we do this is that sometimes we have slippage in the grips of the machine, and we have also machine that is not stiff enough to test the specimen. And in these cases, we can observe in some circumstances that the strain that we measure by measuring the displacement of the machine is usually larger than the actual strain on the specimen. So to come back to the discussion, it is more complicated, of course, to measure strain in addition to load, and it should be measured by methods that are validated. We can use the machine measurements if we couple it with another measuring device or another measuring procedure that can ensure that the machine measurements are accurate. And then going to the data that need more complexity is when we want also to know the strength degradation. What is strength degradation actually? Is the drop of the strength of the material with loads, with the loading. So how can we measure this? Is described here. We need to interrupt the test and perform a static test. What does it mean in terms of, if I start now drawing here my SN curve, imagine that I have a stress, and here I have number of cycles. This is the easy case where I measure the load and I measure the cycles. This is this one for life estimation. When I need to measure also the stiffness degradation, for the same specimen during loading, I also measure the strain, and then I can also give a graph that shows the stiffness degradation with the number of cycles. When I need to know the static strength during testing, it means that for a specimen that is running, I have to interrupt it and do a static strength test, which means that to conclude with a specimen here, we need to test many specimens, so others that are interrupted in between. So we have a specimen here, we stop it, and we do a static strength test. It might fail at this load level. I stop a test there, I do another static test. It might fail at this load level. I draw another one, it might fail there. So finally I have a curve that shows the drop of the static strength with loading. And this is what we call the residual strength methods or criteria at the end. So this, you can imagine, that is the most complicated experimental program related to the other two, and gives this additional information that is used in a lot of cases for design, but probably this complexity sometimes is not enough to justify the need for this investigation. Of course, we might be interested to investigate the damage progress, so the crack density, how the cracks that are developed in the material are accumulated to create damage. And again, this is a quite complicated method, or complicated demand, if you like, for the material investigation, because it's not obvious, it's not easy to measure the crack density. You can again do it with visual methods. You remember before I showed these photos. When the material is translucent, you can take photos with a backlight, and you can see the cracks, the way that they accumulate, and then you can use even a machine learning tool to calculate how much cracks you have. But if the material is opaque and you cannot have a visual measurement like that, then you need to use more sophisticated methods for this type of measurements. So what I will do now, I don't know if yes, I think Professor Bedi, we can probably do the first break here.